So why is that true? Why is it that we're just going to look at the next derivative of my function after the stopping point? Well, the reason for that just comes down to the fundamental theorem of calculus, really. So if it were true that my n plus first derivative here is always less than or equal to some number m, well, then this formula for their integrals has to be true. So if I am taking the integral of some second derivative, say, and that second derivative is always less than the number capital M, then this integral on the right has to be bigger than this integral on the left. What is that integral on the left? Oh, I know an antiderivative already. If I'm integrating the second derivative of some function, its antiderivative is the first derivative of that function. So the fundamental theorem of calculus says that this formula on the left, again, the fundamental theorem of calculus, has got to be less than or equal to m times x minus a. Okay, cool. So this is how it would look like for the second derivative. In general, what's going to go on here for if I stop at the second derivative, if I stop at the third derivative, and so on, we'll see a very similar pattern. So let's work backwards a little bit more. If it was the first derivative of the function I would be integrating, that must be less than or equal to the first derivative of the function evaluated at a plus, this upper bound here. How did I get that? Well, on the previous slide, I just rearranged. So I took this negative f prime of a, and I just moved it over to the right-hand side. Again, this is the kind of thing that you could do for an arbitrary nth derivative. So what does this look like? If I wanted to integrate the first derivative of the function, that would be less than or equal to integrating this other formula instead. So it must be, again, using fundamental theorem of calculus, this formula over here. I know my antiderivative is the original f of x. This has got to be less than or equal to the formula on the right. Oh, so that's going to be f prime at a times x minus a plus m times x minus a squared, all divided by 2. Again, using fundamental theorem of calculus, this is just a constant. This is a constant times a linear polynomial. That's how I get that antiderivative. So what's this? The function f of x minus the function f evaluated at a minus the function f prime evaluated at a times x minus a. Well, what's this? This is an upper bound. So this stuff that I've highlighted in yellow, this is the original function minus the degree 1 Taylor polynomial. Well, that's exactly what I mean by my remainder term. And it is guaranteed to be less than this quantity on the right-hand side.